Okay. So hi Rasika. So I guess we'll get started in 5-10 minutes so that maybe if a few more students want to join, they can join the session. So I guess we'll get started in like 5-6 minutes. So like currently the time is 5-1. Maybe we can get started at like 5-7 or 5-8. Okay, so I guess no one else is joining, so maybe we can get started then. So, once again, hello Rasika and hello to everyone who's watching on YouTube. So, for the last time this semester for NPTEL courses, I'm Lakshya Saggi, the problem solving TA for the Tuesday sessions, and this is the not a problem solving session, but rather the summary session for the NPTEL competitive programming course. And in this will be a short session, like just a 1 hour session, and I'll try to wrap up. I'll just try to wrap up all the contents which we have covered through the whole 12 weeks. So I'll just be briefly reminding you of the topics which you have covered. So it's sort of revision session, not much. So it won't take much. It will be just be a short 1 hour session, and maybe if there are any doubts which you want to ask, you can type via chat. And so we won't be discussing any problems naturally today, but still, if you have any doubts related to any week's lectures or something, maybe if I'm able to help out, I'll try to do my best. So feel free to ask anything via chat. So other than that, maybe I guess we can get started. So I'll just share my screen. Uh, okay, so let me just share my screen. Okay, okay, I think there's an issue. Yeah. Okay, so like I just have a bunch of topics prepared for today, like the topics which we have covered. Just to remind you guys of all the topics. So just let's see how far we have come in this course effectively. So in the first week, actually, we started out with understanding what actually is time complexity. So there were some problems in the in the problem session which were related to time complexity, like how to find out time complexity of functions, and there were some ad hoc problems which were discussed. So what do you generally mean by ad hoc? So ad hoc problems are generally which require some specific solutions, which are not tailor made, like sorting, searching, or which are not famous algorithms, but rather the problems which are somewhat unique on their own. Like you have to solve them using some special properties of the problem themselves. And we also talked about something like winning strategies. And the problems which we covered in this week were basically in the lectures, the problems which are covered were the reverse sort and engineering reverse sort, and the number game and the game will it stop. So these were the problems which were covered, and in the problem sessions we discussed questions related to it. But I don't think there is much to take away from this week, to algorithms for us. So yeah. Then from the second week, a bit of actual algorithmic content started coming along our way. So the second week was focused on sorting and searching methods. So there was this problem which we discussed related to trouble sort. Then there was a problem, the meeting place cannot be changed, magic shift, and simple skewness. So these four problems were discussed in the second week. But uh, maybe on a broad perspective, the focus of second week was on effectively sorting and searching algorithms. So maybe I should just mention this myself. Maybe if you guys already know, or maybe if you guys want to learn further. So for sorting and searching, the main types of topics on which these sorts of problems are based on. So these are the main sorts of sorting algorithms. So sorting algorithms, which if you are doing competitive programming or programming in general, which you should know about, are algorithms like bubble sort, selection sort, quick sort, and merge sort. I believe some of these were discussed in the lectures also, but just to mention to you guys that since the main focus of this week was on sorting and searching, so these are some of the sorting algorithms which one should ideally know about. So these merge sort and quick sort are order n log n time algorithms, whereas bubble sort and selection sort take order n square time in the worst case. But nonetheless, the concepts of these sorts are also important. Like this trouble sort was just a different variation of a bubble sort. Yeah. Similarly, for searching, So for searching algorithms, I don't think there is a lot to know. So there is just a simple linear search which you can do. So suppose you have to search an element in an array, then you can search it via linear search, or another method can be probably binary search. Yeah. So for sorting and searching, which was the focus of the second week, the main sorts of algorithms are this, which one should know about ideally. And the problems were based on like the theory behind these algorithms only. So yeah. And after that, and after the second week, so in the third week and this so in the third week, the focus of the third week was more on greedy algorithms as well as stable matchings. So stable matchings algorithm was also a type of greedy algorithm, but in general, the focus was on like this topic, the greedy algorithms. And maybe what is a greedy algorithm? So maybe I should just mention this. So greedy algorithm. So like a very high level definition of a greedy algorithm would be an algorithm which selects the best possible uh, element available at the moment, or which makes the best possible decision available at the moment. So something like this, like a greedy algorithm is effectively an algorithm in which at any point of time, we just make the best possible decision which we feel is the decision at that point of time. So in greedy algorithm, we don't worry about the future or anything. We just see, okay, so at current point of time, what's the best course of action I can take? And we just take that action. And this is effectively what we call a greedy algorithm. So then there were some examples for greedy algorithms which were discussed. So pancake flipping, islands war, and then there was this stable marriage. So stable marriage can be classified as a greedy algorithm, but the theory of stable marriage and the stable matching like is in itself a whole field of research actually in computer science. So I don't like to put this under just greedy algorithm, but I like to put this as a very different area, like because the stable marriage algorithm is actually under a wide scope of research in computer science. So, but uh, just to remember, like what happened in the stable marriage was it was somewhat of a so men proposed. So when men proposed to women greedily, so we wanted to make a so we wanted a stable marriage, and what was a stable marriage in which the all the married pairs were stable. And what did we mean by stability? That no part no two partners prefer some other married partners instead of their own. So it was something like that. Maybe I don't want to get into the technicality because or maybe I can because we have a bit of time. So yeah, stable marriage, a marriage which is stable, that is does not have a blocking pair. And what was a blocking pair? So blocking pair was something like this. So a pair x comma y, or maybe I can say m comma w because of a man, m stands for man and w stands for a woman, is a blocking pair if there exists another pair m prime comma w prime such that m prefers w prime over w and w prefers m prime. Okay, so Okay, so I think yeah, a pair M comma W is a blocking pair. Maybe what I should write is yeah, is a blocking pair if uh so effectively what does a blocking pair mean? So a blocking pair is nothing but a pair such that both of these M comma W prefer each other over their own respective partners. So suppose maybe I should write it like something like this. So suppose M is married to, let's say, W1. So I should write it like probably like this. Suppose M1 is married to W1 and M2 is married to W2. Then what do you mean by blocking pair? So basically M1 comma W2 will be a blocking pair. So a man and a woman form a blocking pair if both of these man and woman prefer each other over their own partners. So partner of M1 is actually W1, but suppose M1 prefers W2 over W1. So M1 would want to break off this marriage with W1 and go with W2 instead. But maybe W2 has an issue with it. Like W2 does not want to go with M1, but instead wants to go with M2. Suppose this is also not the case. So what if W2 also prefers M1 over M2? Then what will happen is effectively both M1 and W2 will break off their own marriages with W1 and M2 respectively and will run away with each other. And this is something which we don't want. We want stability in marriages. So that's why what we use in stable marriage, we want a marriage which is stable that it does not have a blocking pair. So basically, there should be no pair such that the man and woman prefer each other over their respective partners. So what this means is suppose M1 and W2 is a pair, then it is a blocking pair if and only if M1 prefers W2 over W1 and W2 prefers M1 over M2. So in this case, effectively what will happen is M1 and W2 will run away with each other and will break off their own marriages, which is something which we don't want. So yeah, so that's what we call a stable marriage in which no pair will break off their own marriage. So yeah, and the algorithm for this stable matching, which we discussed, was so stable matching algorithm was somewhat like a men proposed to women greedily. So a high level idea of this algorithm was so all men propose to women in the best order, like the woman which they feel is the best for them, which is at their highest preference. And then effectively women rejects men based on what the choices of women. And like this is what happens in this algorithm. You can just revisit it in the lectures. But this is the sort of high level idea behind it that men propose to women greedily. And this is how we obtain a stable matching pairs. So this is a whole field of research in computer science, actually, stable matchings and the theory behind stable matchings. So yeah, I don't like to put this under just greedy, but rather a whole set of different problems. And examples, and then in the end, we discuss examples where greedy does not work actually. So there were different problems where we discussed that greedy actually does not work, like the problem of coin change or the traveling salesman, etc. So this all was also discussed in the lecture. So yeah, you can revisit this also if you want. But yeah, so we know that greedy algorithm selects the best possible decision available at the moment, but maybe this is actually not correct always. And yeah, so that's why there are examples where greedy does not work. So we discussed some of those examples also. And then came after this in the fourth week. So in the fourth week was mostly based on this very beautiful disjoint set union data structure, which we talked about. And there we talked about different concepts like union by rank. So disjoint set union data structure is used to, so maybe I should just uh, mention this, like used to maintain disjoint sets and query if two elements belong to the same set or not. Used to efficiently maintain disjoint sets of elements. So uh, what this data structure does is actually is it just maintains disjoint sets of elements in form of trees, if you remember. And the query which we can ask this data structure is if two elements belong to the same set or not. And it should also support it should also supports set union operation. So effectively, this disjoint set union data structure is used for two types of queries. So what if we want to ask if two elements belong to the same set or not? And second thing, suppose we want to take set unions. So in the first step, we take union of two sets, and then we want to ask whether two elements belong to same set or not. Then we take union of some more sets, and then we ask again whether there exists two elements belonging to the same set or not, and something like that. So this disjoint set union data structure is used to store and query these sorts of operations very efficiently. So these were very small time operations as we discussed. And the main techniques which were used were something like a union by rank, which was used. So, and also a technique called path compression. So in union by rank was used to reduce the complexity of the union operation. And then this path compression was used to further reduce the complexity, effectively reduce the amortized complexity of this disjoint set union data structure. So this path compression technique does not reduce the worst case time complexity, but rather reduces the amortized time complexity of the data structure. So maybe I should write this also. Yeah. So something like this. And and then we arrive at the concept of what actually does amortized time complexity mean. So we sort of described it in a high level detail. So amortized time is on a higher level is just the average time taken over a long set of operations. So worst case time complexity is, suppose at one operation, what time will I spend? What computation time will I spend at one operation? In amortized time, we are not concerned about the time taken for one operation, but rather are concerned about the total time taken over a series of operations. So example is, suppose we have Q queries for a problem. So suppose we have a problem and we have Q queries scheduled for it. So there will be Q question asked in the problem. So suppose the first query takes order Q time. So resolving the first query takes order Q time for us. And then the next Q minus one queries, let's say, take only order one time each. So resolving the first query, suppose, takes Q time, and next Q minus one queries take only one time each. Then we can first of all say that then the first case complexity is nothing but order Q. And why is this order Q? Because worst case complexity is the worst complexity over all the operations. So first query took Q time and the next ones took order one time. So the worst case is actually this order Q time. But note that it is not too bad for us, because actually the average query time, which is the amortized time, will come out to be very low. So how do we find out the average query time? Average query time, or the amortized time, is nothing but uh, the sum of time taken over all of these queries So over all these queries, we just take the sum of the time taken. So one query took q time and the remaining q minus one took only one time each. So this was the sum total of the over sum total of times over all the queries divided by the number of queries. So we are just taking somewhat of an average over all the query times. So there is one query of q time and next q minus one queries of one time. So what will be the average? So it will be 1 times q plus q minus 1 times 1 divided by q. And this will come out to be approximately equal to 2, which is a constant. So amortized time complexity here will come out to be order 1. So even the worst case time complexity is order q, amortized time complexity comes out to be order 1. Suppose in this in this type of problem. And this is something which we observe when we use path compression technique also, that amortized time complexity becomes very low. So this is also a very important notion which one should know about, the amortized time complexity. And maybe if you want to read about it further, uh, maybe let's just leave it at that. Like, I don't want to get into that, but yeah. And then there were some applications of this disjoint set union data structure which were discussed in the lectures, like the destroying array problem or the war problem. So yeah. So this wrapped up the contents of the fourth week for us. And then in the fifth week, we started with some new notions which you may have or may have not known about before. So fifth week was focused on introduction to graphs, BFS and DFS. So what is BFS? So maybe I should write down what is BFS also. So BFS is breadth first search and DFS is depth first search. So in the fifth week, so there was introduction to graphs. So effectively, we learned about what are graphs. So graphs is nothing but a collection of edges and vertices, right? And then what is breadth first search and what is depth first search on a graph. So these are just traversal techniques for the graph, and we learned about them also. So, and then we also learned about what are connected components in an undirected graph. So there are two types of graphs, directed and undirected. In directed graphs, edges have directions. In undirected, as the name suggests, edges don't have direction. So in undirected graphs, we have the notion of these connected components. And what does this mean? A component C is a connected component of the graph G. If either the size of C equals to 1, which means that the number of vertices in the graph is only 1. Suppose there's only one vertex in the graph, then we'll call it one connected component. Or if there are more vertices, then for any two vertices u, v in C, there should exist a path between u and. So on a high level, what does connected component mean? Connected component means in a component where all vertices are connected with each other. And this is sort of the formal definition for that. Suppose there are more than one vertices. So if there is only one vertex, then like obviously that vertex is connected to itself. But if there are more than one vertices, then for any pair of vertices, there should exist a path between those vertices, right? That's when we will say that those two vertices are connected with each other. And this is what the definition here for the connected component suggests. So yeah. And then there was also this important handshaking lemma, which one should know about in graphs. Like this is a very important lemma. Like, it's not too difficult to prove, but still, this is something which one should know. That always so we are talking about undirected graphs here. The number of odd degree vertices in an undirected graph is even. So let's dissect this statement again. So first of all, I hope everyone knows what's the degree of a vertex in a graph. Degree is just the number of edges connected to that vertex. And suppose we have an undirected graph, then handshaking lemma says that the number of odd degree vertices. So the number of vertices having an odd degree in the graph will be even. So what this effectively means is that if we just take every vertex and take the count of the vertices which have odd degree, so a vertex can have either odd degree or even degree, right? So if we just take count of the vertices having odd degree, then this number of vertices will come out to be even. So effectively, what this sort of thing suggests is that there can never be a graph which has only one vertex of odd degree, or just three vertices of odd degree, or five vertices of odd degree. So the number of odd degree vertices can only be 0, 2, 4, 6, 8, or 10. Note that we are not restricting the degrees. Degrees can be anything, but the odd degree vertices, the number of odd degree vertices will always be 1. So this is something which is known as handshaking lemma. And we did the proof for this in the problem solving session for the week 5 also. And it was not too difficult to prove, but yeah, it's a lemma which has a lot of consequences in graph theory. And then after introduction to graphs, after all this, there were some applications. And one very important application which we did in the lectures was testing bipartiteness of a graph. So there was this problem, suppose we are given a graph and we need to check whether the graph is bipartite or not. So, and yeah, but what does bipartite mean? Bipartite means is that can we divide the graph into divide the vertices of the graph into two sets of vertices such that all the edges of the graph lie between the sets only, not uh, inside the sets. Like, I hope everyone remembers like what bipartiteness is, because bipartite graphs are also very important generally in graph theory. So one application was testing whether the graph is bipartite or not, and it was done using BFS. Like we tested this using BFS, and I hope you remember it, guys. If you don't, then maybe you can uh, watch the lecture video for this again. But this is one very important application for in graphs, like testing bipartiteness. This is a very famous problem and a very important one also. Okay. And then in the 6th week, we start. So in the 5th week, we came with introduction to graphs. We did what was BFS, what was DFS, and now we further mentioned some. We further came across some more notions in graph. So effectively, shortest paths in graphs. So suppose now we have weights on all the edges also. So effectively, every path, every edge has a length also. And now we want to find out from one vertex to another the path of the shortest length. So for that, we discuss some algorithms. So first of all, so there were different variants for the shortest path problems. So the first variant which we discussed was the single source shortest path problem. So in this, what is given to us is we are given a single source S. So we are given a single source, and we need to find out the shortest path of all the vertices of the graph from this source. So maybe I should mention this also. From a given source S, find the shortest, maybe I should like this. Given a source S, find the shortest path length from S to all vertices of the graph. So what this means is that effectively we need to find n path length. So what we need to find is the shortest path from S to V1, S to V2. Suppose vertices are V1, V2, V3 till Vn. Then we need to find out the shortest path length from S to V1, S to V2, S to V3, S to V4 till S to Vn, and sort of effectively output this array of length n. And this is called the single source shortest path problem. So for this problem, the first algorithm which we discussed was Dijkstra's algorithm, which is a very efficient algorithm, but there are some drawbacks to Dijkstra's algorithm. So drawbacks are, so what drawback of this Dijkstra algorithm is, so this is very efficient, but it has some drawbacks, but has drawbacks. Like it doesn't work on negative weight edges. So Dijkstra's algorithm only works if all the edges of the graph have positive weights. So we discussed some examples also where if a graph has a negative weight edge, if an edge has a negative weight, then Dijkstra's algorithm fails actually. So it is not very general, like it only works. So it works for a large class of graphs in which all edges have possible weights, then we can do Dijkstra's algorithm. But suppose there are some negative weights, then we can modify Dijkstra's algorithm. So Dijkstra's algorithm can be modified, and it works on graphs with negative weight edges. So actually, there is a modified version of Dijkstra's algorithm which works on graphs with negative weight edges, but it is not efficient. Also, it does not work for negative weight cycles. Or maybe we should not mention this. So yeah. So what modified Dijkstra does is in modified Dijkstra, like this was also covered in the lectures. This is not very well known or very well used algorithm because like yeah, there are much more efficient versions. But what this does is like it works on graphs with negative weight edges, but it is not efficient. Like we cannot bound its time complexity either. So we don't like to use it in practice either. So this is just a theoretical thing, but not used in practice. So what do we do in practice instead is one of these things. So Bellman-Ford is very useful for single source shortest path with negative weight edges. So after Dijkstra, the second algorithm which you should remember is this Bellman-Ford algorithm. Maybe you can forget about this modified Dijkstra, but this Dijkstra is important when all edges have positive weights, then this is the fastest known algorithm. But suppose the edges have some negative weights also, then the best algorithm, which you guys should be doing, is then Bellman Ford is the one of the best algorithms known. So it is useful for single source shortest paths with negative weight edges. It has a time complexity of something like order mn, and this has been discussed in the lectures also. So yeah, so these two algorithms is something you should know about. And then we came about another variant of shortest path problem, which was all pair shortest paths. And what does all pair short what does and what this problem entails is that so in the single source shortest path, we were given a source S and we had to find the shortest path length from S to all the vertices. But in the all pair shortest path problem, we have to find the shortest path length from every vertex to the other vertex, every vertex to every vertex. So there are n square pair of vertices. So we need to find basically n square length, like shortest path from every possible vertex to every other possible vertex. And naturally, one easy way for the doing this algorithm would be just running maybe the single source shortest path algorithm for all possible sources. But that turns out to be a bit inefficient as compared to this algorithm, which was also covered in the lectures, which is the Floyd-Warshall algorithm. This algorithm takes something like order n cube time, and it works with negative weight edges also and stuff like that. And yeah, this is a very efficient algorithm for all pair shortest path setting, the Floyd-Warshall algorithm. Yeah. And then maybe we covered the applications for the shortest paths in graphs. One of the example problems was page hopping, and like yeah, you can view these in the lecture videos also, and etc. And we discuss some problems about these also. So yeah. And then came the seventh week. In the seventh week, so in the sixth week we wrapped up the shortest paths in graph, and then in the seventh week came the notion of minimum spanning trees. So what's a spanning tree? So spanning tree is a notion which occurs only. Maybe I should define this also. So spanning tree is a notion which occurs in undirected graphs only. And what's a spanning tree in undirected graphs? A subgraph of the a subgraph G prime of the original. So what is a subgraph? Subgraph is a graph which has a subset of edges from the original graph, but all the vertices. of the original graph is a, suppose the original graph is G and the subgraph is G prime, is a spanning tree of G if and only if the vertices of G prime, vertices of G prime are the same as vertices of G, and the and G prime is connected as well as acyclic. So effectively what a spanning tree is, informally speaking, is just a subgraph of the original graph. So it's just a set of edges from the original graph such that those edges connect all possible vertices of the graph, and these edges do not form a cycle. So this is what we call a spanning tree. And now what's a minimum spanning tree? So minimum spanning tree is nothing but a spanning tree of minimum possible cost. So yeah. So naturally, if there are n edges, and suppose if there are n vertices, and the spanning tree is acyclic, so the number of edges in a tree is n minus 1 if there are n vertices, right? So number of edges in a spanning tree is always n minus 1. So this is something which can be easy to see. So number of edges in a spanning tree is always n minus 1. And what's the minimum spanning tree? Is just the spanning tree of minimum possible cost. So suppose every edge has a cost associated with it. So the edges which we select in the spanning tree will contribute some cost. So we need to find out the spanning tree of minimum possible cost. And one thing to note is that there can be multiple minimum cost spanning trees for a given graph. So we covered some examples for this also in our problem solving session. But the cost of all those minimum spanning trees will be the same. So the minimum spanning tree need not be unique. There can be multiple trees which are minimum spanning trees. But the cost of all of these trees will be the same. The minimum spanning tree cost will be unique, but the minimum spanning trees themselves can be multiple in number. And it can, like, we covered a lot of examples for this also, and I hope it's easy to see. And this is a very important thing to note because, like, someone can ask you whether minimum spanning tree is unique or not, and someone might get confused. So yeah. So now after this we covered, so like we know what minimum spanning tree is and how do we actually find out minimum spanning trees in a graph. So there are two very efficient algorithms known for it, which are Prim's algorithm and Kruskal's algorithm. So these both algorithms are generally used, like depending on the use case. Both of these are used to find minimum spanning trees in undirected graphs, and both of these are very efficient algorithms. And then we saw some applications for this minimum spanning trees problem, like the island hopping problem, etc. And like you can view the lecture videos for it. So yeah. Okay. So these were some introductory concepts like shortest path, spanning trees, and all. And then in the eighth week, we came into some more advanced concepts of the graph. So the maximum flow in a graph. So this is somewhat of a more advanced concept. And yeah, so I hope everyone remembers what a flow is in the graph and what's a maximum flow. So I'm not going to go through the uh, definition here because I think, yeah, flows are a bit of an advanced concept. So you can see the definition yourselves. So, and for maximum flows in the graph, we learned about the Ford Fulkerson algorithm, which helps us find out the maximum flow. Then we also learned about residual graphs, like what are actually residual graphs. So with respect to a flow, we can always make a residual graph. And in a residual graph, what we do is we just add another edge. So in the forward edge, we just reduce the capacity of the forward edge by the amount of flow going through that edge. So maybe I should mention this here. Suppose an edge carries a flow F. Suppose an edge of capacity C carries a flow F. Then in the residual graph, the forward edge has a capacity of C minus F and backward edge has a capacity of C of F. So this is how we make a residual graph out of a flow. So suppose we have a flow given to us and the edge had a capacity C and the flow carried through that edge was F. Then the residual graph forward edge will have, the forward edge is the edge in the direction of the original edge, will have a capacity of C minus F. So we reduce F from the original capacity C, and in the backward edge, we add a capacity of F. So yeah, this is how we make residual graphs. And yeah, this is also a very important concept in the notion of flows. And then we discussed another algorithm to find max flow. So it was just a modification of Ford-Fulkerson algorithm, which is called Edmonds-Karp algorithm. So Edmonds-Karp algorithm is generally famous because it is somewhat more efficient than Ford-Fulkerson algorithm, even though it involves same principles. So yeah, and we saw some applications of the max flow problem, and one very famous application for this is finding out the maximum matching in a bipartite graph. So yeah, so in a bipartite graph, suppose you have to find the maximum matching, and I hope everyone remembers what a matching is. Like this is some, so this is not stable matching, but we just want to find out the maximum matching. And we can do this via maximum flows, and this was also covered in the lectures. So yeah. So this is also a very important application. So one should know about this, I believe. Okay. So then after this, so we did not entirely wrap up maximum flows in the eighth week because like flows is a very hotly studied topic, is a very deeply studied topic in literature. So then comes the relation of maximum flows to minimum cuts. In the ninth week, we discussed what are cuts and what are minimum cuts actually. And then we discussed the max flow min cut duality. And what does this duality state? It's a very important result in theory of computer science. It just states that the maximum flow in a graph, the value of maximum flow in the graph is actually always equal to the value of the minimum cut in the graph. And this is like one of the cornerstone results of computer science. So yeah. And another thing one should always know about in minimum cuts is like spanning trees in minimum cuts also, there can be multiple ST minimum cuts in a graph. So a minimum cut is just a cut of the minimum cost. So the minimum cost will be the same. So minimum cost will be unique for all the cuts for the minimum cut, but there can be multiple possible minimum cuts. Like in spanning trees, we said that there can be multiple spanning trees, but all of their costs will be unique, but the minimum spanning tree cost will be unique. Similarly, what we can say here is the minimum, there can be multiple minimum cuts in a graph, but the cost of all those cuts will be unique. Yeah. So obviously, like this follows from the definition of the minimum cuts. So yeah, something like that. And we discussed example for this in our problem solving sessions also. So yeah. And here then we discuss some applications for the maximum min-cut duality. And again, I believe I've been repeating this narrative a lot, but yeah, the one application here was the finding out the vertex cover in bipartite graphs. And this is also a result which one should know about. Like this is also very important result. Like how do we find out vertex cover in bipartite graphs using max flows and min cuts? So like I believe the main objective of the session is to put things into perspective. Like you have learned a lot of things, but maybe I'm just reminding you guys like what are the most important things which you guys have to take away. Like if one has to take away, if one has some takeaways from this course, so what are the takeaways? So in max flow, like residual graph, Ford-Fulkerson, Edmond-Karp, and this maximum matching in bipartite graph. So these are very important takeaways which one should know about. Similarly, in maximum min cuts, this is a very important takeaway. So there might have been other problems discussed also in the lectures related to max flows min cuts, but these are some of the more standard and the most important things which one should know about. So yeah. Okay, then after this ninth week came the 10th week, and from 10th week onwards, we just shifted our focus entirely from these graphs to dynamic programming. So in the 10th week, there was this introduction to dynamic programming. And what is dynamic programming? We learned that a method for solving problems by breaking them into smaller sub-problems and storing the results of some problems to avoid redundant computation. So this is what we call breaking into smaller sub-problems as finding the inductive structure, and storing the results of sub-problems is what we call the memoization technique. So yeah. And then we learned about that there are two types of dynamic programming approaches: the top-down dynamic programming and bottom-up dynamic programming approach. So yeah, and then there were some practice problems based on that in the 10th week. Then from 11th week onwards, we did not have any lectures. We did not have any NPTEL lectures, but rather we had some problems which we discussed in the problem solving sessions. So these are some very famous dynamic programming based problems. So I've just mentioned like what are the problems which one should take away and one should know about, like about these problems, because these are all again very important problems in computer science. So in the 11th week we covered problems like longest increasing subsequence. This is a very important problem. Similarly, another problem which we discussed was longest common subsequence. So I hope you guys remember what these problems are. So in longest increasing subsequence, we have to find, given an array, the length of the longest subsequence, which in which all elements are in increasing order or in non-decreasing order. Similarly, in longest common subsequence, we are given suppose two strings, and then we have to find out the substring which is common to both the strings and it is longest in length. These two were some two of the important problems which we discussed in the 11th week's problem solving session. And then in 12th week again we discussed some dynamic programming problems, and the main problems which we discussed, like which you should know about, are the shortest paths in grid. So we just did this yesterday only, right? The shortest paths in grid problem, where we had crosses and a horse could only hop across the cross, and yeah, something like that. So these types of shortest paths in grids problems. So there can be multiple possible problems like this. So these types of problems are also generally asked in dynamic programming and stuff like that. And then another problem which is quite common in dynamic programming is this matrix multiplication order problem, which we discussed again yesterday, that suppose there are n matrices m1 to mn, and in what order should we multiply these matrices to minimize the amount of scalar multiplications. So yeah. So we discussed these two problems yesterday itself. So I hope you guys remember this. So yeah, so these were again important problems which you will generally come across in the future if you give any test or something like that related to dynamic programming. Okay, so I guess uh, this wraps up the 12 weeks worth of content which we studied uh, in the in the whole in this whole semester, NPTEL semester. Note that this list is not exhaustive, obviously. Like I have not written like everything which we have studied, but rather I have sort of tried to write down the main takeaways from this course, which one should have after uh, like after going through this course. One should know about minion spanning trees. One should know about shortest paths. One should know about max flows, max flow min duality, and these applications and stuff like that. So initially, we just discussed some ad hoc problems. So you may not remember these problems in the future, but these approaches, these sorting algorithms, searching algorithms, and stuff should be something which you guys should know about even after this course ends. So yeah. Okay then. So yeah, I guess this is it from my side, guys. So I think we have 2-3 minutes left with us. So if anyone has any comments, any doubts, or anything, uh, I don't know much about the administrative stuff, but if you have anything, maybe you can ask me via chat and I'll try to answer this. I'll try to answer it in the remaining 2-3 minutes. Okay, so Ram is typing something in the chat. Okay, again, Ram, I'm just a problem solving TA, so I don't know much about the final exam, the what will be the format or the venues or something. Maybe you will have to ask the in the NPTEL discussion forum or maybe on the Discord. I think there's a Discord also for the Discord channel also for the course. Maybe you'll have to ask any administrative doubts there. Like I can only resolve doubts related to the problem solving sessions. So sorry for that. But I believe in the final exam, one thing I can ensure you is that assure you is that the problems will be similar to the ones you have done in assignments and in the problem solving session. So believe me, if you have gone through the lectures and the problem solving sessions and did the assignments carefully, then you will be able to easily crack the final exam also. The problems won't be much different. The theory will all be the same, and yeah. So just trust me that the material you have is enough. You just need to go through it uh, carefully. So yeah. Okay then. So I guess this is it, guys. So we are close to the closing time of this session also. So once again, so since this was the last session for this course this semester, so I guess thanks everyone for watching this video and attending these sessions. So this kind of wraps up our whole NPTEL comparative programming course for now. So yeah, I hope you enjoyed these videos and yeah, good luck for the exam, everyone. So yeah, Ram is asking if this video will be available on YouTube. So yes, Ram. So I will upload this also. I believe you guys already have the links to all the lecture videos, right? So I'll upload this video also, and you will get the link to this lecture video also. So this problem solving video also, summary of this session also. So I'll be sharing this by tonight itself. So I'll be sharing this document also on the Drive link which we have, and I also share the recorded video of this session on YouTube. So yeah. So okay, I guess this is it, guys. So maybe we can now close the session. So I'll just stop recording. So once again, thanks everyone for attending through these sessions, and yeah, hopefully I'll see you guys next semester in some other NPTEL course also. So maybe I'll just stop sharing my screen, guys. Thanks, Rasika and Ram, and all the best for your exam, obviously. So, so bye bye, guys. See you maybe next semester.